Okay, the next question says the quantity of heat required or needed to freeze 1 kilogram of milk at its freezing point is known as dash. A heat capacity. The question is asking the quantity of heat needed to freeze 1 kilogram of milk at its freezing point. It's called, so in the options, we have heat capacity. So can it be heat capacity? No. Heat capacity is the quantity of heat required to increase the temperature of a substance by 1 degree. So it doesn't go with it's not quantity of heat required to freeze 1 kg. So it's generally the quantity of heat required or needed to increase the temperature of a substance by 1 degree. For instance, if a substance has a temperature of 25 degrees Celsius, yeah, to increase it to 26 degrees, that is by 1 degree, how much heat do you need? How much heat should you apply to lift its temperature by 1 degree? That is heat capacity. Heat capacity. Then it is not about the heat required to freeze 1 kg of milk or to freeze 1 kilogram of a substance. No. Then B is a latent heat of friction. Latent heat of friction. So let's see what latent heat of friction is about. Latent heat of friction. I think we mentioned this in one of the previous examples. So that latent heat of friction generally is the heat required to melt. Friction, it has to do with melting. You understand? So the case of freezing, when we say freezing, is it actually melting? So heat required to freeze 1 kg of milk. Milk is a liquid. The freezing is a process of solidification. So why fusion has to do with melting. So the heat required uh, to melt a substance is the latent heat of fusion. So this is also not the answer in this case. Like I said, freezing is solidification. So you are trying to solidify. But fusion, you are melting. Think think I'm correct. So now let's go to the next option. The next option says specific latent heat of fusion, which is the same thing as it, but this time around, this is very specific, which means for 1 kilogram to melt 1 kilogram. Then it is also not the answer. Then we have the specific heat capacity. Specific heat capacity is just like heat capacity, but now the heat capacity per kilogram. The heat required to raise the temperature of 1 kilogram or a unit mass of a substance by 1 degree. So if you look at the question, it appears like none of the options fits it. It it looks like it would have been specific latent heat of fusion. For us to have 1 kg, then that means that is specific. Then because we are converting at the freezing point, we are converting at the point of, it has to do with convection. We need a latent heat. So the answer is supposed to be latent heat, uh, latent heat of freezing You understand? Or latent heat of solidification, but really that one does not. So we'll go for latent heat of fusion. But actually, fusion is all about, like we have latent heat of fusion of ice, melting of ice. So specific latent heat of fusion will be the closest answer in this case. So, but if the process here, the change, phase change here is about solidification. But in absence of, it should have a specific latent heat of freezing. But that appears to be uncommon. So if you must choose an option there, then the closest is the specific latent heat of fusion. Why it is not latent heat but specific is because 1 kilogram is involved. So whenever it is about 1 kilogram, then specific has to come in the name. If the question had said the quantity of heat required to raise the temperature of 1 kilogram of milk, then that would have been specific heat capacity. So let's go with that. That's number number 6 from this side. So let's check on the next question. The next question is saying, in a certain process, in a certain process, 12,000 calories in internal energy. Note 1 calorie is equal to 4.184 joule. So the question doesn't make sense. It's not a complete question, but I mentioned the, the typing of the question has a lot of problem. So this question is not directly, it's not, it's was extracted from the Jamb past questions and typed with a lot of errors. So what my search gave is the question is, in a certain process, 12,000 calories of hexane is supplied to the system, which the system does work, while the system does work 7500 joule. So that is 12,000 calories of what? Of hexane is supplied to the system, which, while the system does work, then the work done. This is the quantity of heat supplied. Then the work done is 7575 joule. That's the work done. So when this heat is applied to the system, it does a work equals to 7,500 joule. And the question is, calculate the power developed. No. The question is, find the change in internal energy. Eh? Find the change in the internal energy. That's the question. Given that 1 calorie is equal to 4.182 joule. Sorry, 4.184 joule. So we have this particular process where a quantity of heat Q, that is trying to solve this question, the quantity of heat Q supplied is 12,000 calories. Calories are alternative units of heat. You can use joule, calorie, and others. So we are given a deconversion factor. Now 1 calorie is 4.184 joules, which means 1200 calorie will be what in joule will be 1200 times 4.184 uh, joule. So that should give 12,000 multiplied by 4.184. That gives 50,208. 5208 joule. So this is the quantity of heat supplied to the system, and it does a work W equals to 75000 joule. So why we need to do the conversion is because work is given in joule. There must be unit consistency. So we can't be using calorie here while we are using joule here. So we must either convert both to calories or we work with joule. So that is the essence of this conversion factor. Then the question now says we should find a change in the internal energy. So the change in the internal energy as this quantity of heat supplies produces a work equals to 75000 change. So symbolically, the change in internal energy is delta U. Internal energy is signified U. The internal energy, the total energy in the system. Then if there is a change, which means initially the system has a particular energy, is at a particular state, and then on applying this heat, this work is done. So the system must have been, you know, disturbed. So and there will be change in the internal energy. Then what is then the change in the internal energy as this happens? So the formula is that we are going to do this by subtracting work from the quantity of heat supplied. So it is as simple as the quantity of heat supplied minus the work done. It is like a system. Um, I think we don't need to make use of this. You can claim. So if I have a system, let's say this is a system with its boundary. Outside the system is what we call the surrounding. Eh? The system's surrounding. So if this is an open system, then work, which means this system is open to what do I call it? To mass and energy. So work, a quantity of heat is supplied as an input into the system. This is the heat. And then it gives an output, which is the work done. And this system has an energy, an internal energy. So which must have changed as heat enters it and work goes out of it. So the internal energy must have changed, and the change in the internal energy is what you have to find. So it will be simple by simple energy balance. By simple energy balance is that if you want to do energy balance and know what are the difference, the balance, then we will say okay, Q enters the system, then work leaves it. So then the difference between what enters and what leaves should be what is inside the system. It is like you have a bucket of water. Let's say initially it has a certain volume. Let's say V1. Then you not on a tap and run water into it. And then there is an exit tap here that you open it to let water go. So you introduce a certain quantity of water and a certain quantity of water goes out. So if you want to know what is left in the system or what has changed in the volume of the system, so what we do is we take the difference between what enters and what goes out. So that is exactly what we apply here. That if you want to know the state of the system, this change in the system, that it is actually the difference between what enters minus what leaves. So if we remove what goes out of the system from what enters the system, then the difference is what is retained, is the state of the system. So that's the essence of using this formula. So this problem is that of thermodynamic. So where you have some terms like the internal enthalpy change, the internal energy change, quantity of work done, the quantity of heat applied. K will always represent heat energy. Then W always represent work. U internal energy. Then you might say H. Say H is an enthalpy. Delta H is represent an enthalpy change or what you call heat change. So if we go by this formula, then we directly substitute 50,000 of 208 minus 7500. So I think that gives whatever it gives, and that is the answer. 50,208 minus 7500. That gives 42708. 42708 joule. So because it's a larger value, you can convert to kilojoule by dividing by 1000. So it should give you, if you divide by 1000, it should give you 42.708, which we can simply put as 42.7 kilojoule as the answer. I hope this is clear. So we have 42708 joule. Actually, in the options, they give the answer in joule. They did not convert to kilojoule. So whichever way, that's the answer. So question number 8 says some water is heated in a pot. The major mode of heat transfer within the water is or are by A. Convection, B. Conduction, C. Radiation, D. Conduction and radiation. Let's treat that. So this is a case that has to do with heat transfer. Like it said, there is maybe a topic of physics that is about heat transfer, and it is as simple as the English heat transfer. So with the movement of heat from one point to another is a heat transfer. So to summarize it all, there are modes by which heat transfers from a point to another. So the modes of heat transfer are conduction. So heat can transfer by conduction or by convection or by radiation. So these are the three major means by which heat transfers from one point to